Fundamentals, part of the Ceragon installation and commissioning course. This module introduces the radio relay principles, the propagation affecting parameters and other important aspects regarding the radio interface that is crucial for a microwave communication system. Summary. In this module we will discuss about radio relay principles, modulation, adaptive coding and modulation, ACM, and mean square error, MSE, SNR and bit error ratio, transmission techniques such as cross-polarization interference cancellation, spatial diversity and line of sight multiple in, multiple out. Radio relay is a system of communication employing electromagnetic waves propagated through space with the speed of light. The wavelength is determined by the frequency as the ratio between the speed of light through vacuum and the frequency. The radio frequency spectrum goes from 30 Hz up to 300 GHz and is split into radio waves, from 30 Hz up to 3 GHz, microwave, from 3 GHz up to 30 GHz, and millimeter waves, from 30 GHz up to 300 GHz. Here you may see the complete electromagnetic spectrum, containing radio waves, from 30 Hz up to 3 GHz, microwave, from 3 GHz up to 30 GHz, millimeter waves, from 30 GHz up to 300 GHz, and sub-millimeter waves, such as infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays. Take a closer look at the correlation between the frequency and wavelength, where the name of the waves are coming from. Also please take note of the names of the bands that are to be explained. Here is a list of the radio frequency bands, names, wavelengths and their utilization. Extremely low frequency, ELF, or ITU band number 1, has a span from 3 to 30 Hz, a wavelength from 100,000 to 10,000 kilometers and is used for submarine communication. Super low frequency, SLF, or ITU band number 2, has a span from 30 to 300 Hz, a wavelength from 10,000 to 1,000 kilometers and is also used for submarine communication. Ultra-low frequency, ULF, or ITU band number 3, has a span from 300 Hz to 3 kHz, a wavelength from 1,000 to 100 kilometers and is used for submarine and mine communication. Very low frequency, VLF, or ITU band number 4, has a span from 3 Hz to 30 kHz, a wavelength from 100 to 10 kilometers and is used for navigation, time signals, submarine communication, wireless heart rate monitors, geophysics. Low frequency, LF, or ITU band number 5, has a span from 30 to 300 kHz, a wavelength from 10 to 1 kilometer and is used for navigation, clock time signals, AM long-wave broadcasting, Europe and parts of Asia, RFID, amateur radio. Medium frequency, MF, or ITU band number 6, has a span from 300 to 3,000 kHz, a wavelength from 1 kilometer to 100 meters and is used for AM, medium wave, broadcasts, amateur radio, avalanche beacons. High frequency, HF, or ITU band number 7, has a span from 3 to 30 MHz, a wavelength from 100 to 10 meters and is used for shortwave broadcasts, amateur radio and over-the-horizon aviation communications and radars, RFID, radar, automatic link establishment, ALE near vertical incidence skywave, NVIS, radio communications, marine and mobile radio telephony. Very high frequency, VHF, or ITU band number 8, has a span from 30 to 300 MHz, a wavelength from 10 to 1 meter and is used for FM, television broadcasts and line-of-sight ground-to-aircraft and aircraft-to-aircraft communications, land mobile and maritime mobile communications, amateur radio, weather radio. Ultra-high frequency, UHF, or ITU band number 9, has a span from 300 to 3,000 MHz, a wavelength from 1 meter to 10 centimeter and is used for television broadcasts, microwave oven, microwave devices and communications, radio astronomy, mobile phones, wireless LAN, Bluetooth, Zigbee, GPS and two-way radios such as land mobile, FRS and GMRS radios, amateur radio. Super high frequency, SHF, or ITU band number 10, has a span from 3 to 30 GHz, a wavelength from 10 to 1 centimeter and is used for radio astronomy, microwave devices, communications, wireless LAN, most modern radars, communications satellites, cable and satellite television broadcasting, DBS, amateur radio. These are the microwaves. Extremely high frequency, EHF, or ITU band number 11, has a span from 30 to 300 GHz, a wavelength from 1 cm to 1 mm, and is used for radio astronomy, high-frequency microwave radio relay, microwave remote sensing, amateur radio, directed energy weapon, millimeter wave scanner. These are the millimeter waves. Tremendously high frequency, THF, or ITU band number 12, has a span from 300 GHz to 3 THz, a wavelength from 1 mm to 100 micrometer, and is used for terahertz imaging as replacement for X-rays, ultra-fast molecular dynamics, condensed matter physics, time domain spectroscopy, terahertz computing, communications, sub-remote sensing, amateur radio. These are the sub-millimeter waves. This image shows how radio waves are propagated through atmosphere, either as a direct wave, reflected wave, or refracted wave. The electromagnetic waves that Ceragon deals with are propagated lower than the stratosphere and are found on the lower side of the screen. The propagation of said waves is most of the times direct, within a radio line of sight, but phenomenon like the reflection of EM waves and the refraction are affecting their propagation. We will cover these effects a little later in this same module. A radio link is the real-time communication between two transceivers which operate within a frequency division duplex channel between the two end stations. That means that both radios operate on receiving and transmission at the same time, on two different frequencies that are part of the same channel. The commonly used frequencies for microwave communication are in the range of 4 to 90 GHz. In the following we will clarify the terminology used in microwave communication. A duplex radio channel is a frequency division duplex communication system that occupies two frequencies, one per way. The duplex distance in frequency between the frequency pairs is wide enough to avoid interference, and depends on the working frequency band. Let's see what is the meaning of high and low station. A high station is the endpoint transmitting on the highest carrier frequency. This endpoint is receiving on the other carrier frequency that will be lower. The opposite situation is available for the low station. This station transmits on the lower frequency from the paired frequencies. Geographical displacement used for avoiding overshooting. In frequent scenarios, the operators need to reuse the frequency channels when planning a microwave network or a chain of microwave network elements. In such scenarios, we always have the risk of creating interference over the same channel between the elements that are situated, like shown below, in a straight line. As low transmitting elements would interfere with other high elements in a straight line, over one hop, we recommend you use this type of arrangement, not in straight line, to minimize the risk on interfering with the next link. This can be useful for the case of elements installed on straight highways or roads. Microwaves travel in straight lines and they can be focused and reflected just as light rays can be. A feeder receives the microwaves from the waveguide and then transmits them through a parabolic dish's reflecting surface to the other side of the link. The wavefront reaches the reflecting surface of the antenna, and then it leaves the antenna in parallel paths. Because of the special shape of a parabolic surface, all paths from source to the reflector and back to end user are the same length. This diagram, which has antenna gain vertically and frequency band horizontally, will give frequency ranges, approximate antenna gain and relative antenna size. The diagram verifies that radio link antennas are with a gain between 30 to 50 isotropic decibel and that lower frequencies demand for larger antenna diameter. Please note that the diagram is not accurate enough for link budget calculations. Precise antenna gain figures can be found in data sheets. Main parabolic antenna types. Standard performance antennas, SP, are used for remote access links with low capacity. Reusing frequencies on adjacent links is not normally possible due to poor front-to-back ratio. High performance antennas, HP, are used for high and low capacity links where only one polarization is used. Reusing frequencies is possible. cannot be used with co-channel systems. High-performance dual-polarized antennas, HPX, are used for high and low-capacity links with the possibility to utilize both polarizations. Reusing frequencies is possible. Can be used for co-channel systems. Super high-performance dual-polarized antennas, HSX, are normally used on high-capacity links with the possibility to utilize both polarizations. Reusing frequencies is possible with high interference protection. Ideal for co-channel systems. Ultra-high-performance dual-polarized antennas, UHX, are normally used on high-capacity links with high interference requirements. Reusing frequencies in many directions is possible. Can be used with co-channel systems. Antenna polarizations and classes. For single polarized antennas, the antenna polarization can be changed by turning the antenna feeder 90 degrees. Just as the single polarized, the dual polarized antennas are available for integrated mount with the radio units. The lower left shows such an installation. For increased interference suppression and thereby increased frequency economy, dense super high performance antennas are used. These antennas meet the specification for side lobe suppression according to ETSI Class 4. The diagram shows the approximate difference in side and back lobe suppression between high-performance antennas according to ETSI Antenna Class 3, yellow, and super high-performance antennas according to ETSI Antenna Class 4, green. 45 isotropic decibel has been chosen as example for the main lobe gain. When terrain does not permit line-of-sight transmission, some passive repeaters can be used. Please observe in the slide presented, two different scenarios of a passive repeater usage. In the first example, on your left diagram, you can see a passive repeater like the one on the right picture, a reflective material used on a mounted support that allows for the electromagnetic waves to be propagated at a certain angle, because the line of sight cannot be achieved. Next to it, onto the same diagram, you can see the second scenario, where a back-to-back antenna installation is used because of the same reason. No direct radio line of sight could have been achieved. Both examples serve the same purpose, it's just a matter of client preference due to cost, tower height or the specific location. E-band is already a proven and mature technology in commercial use since the 1980s. Ceragon machines operating in E-band can use 10 GHz of radio spectrum, between 71 to 76 GHz and 81 to 86 GHz. E-band radio links require direct radio line of sight. Advantages of E-band over traditional microwave bands. It utilizes a large radio spectrum, easily producing gigabit throughputs. It is uncongested, still, practically new worldwide, with operators just understanding how to utilize it. It has fast and inexpensive license with smaller costs than traditional microwave channels. Due to the pencil width characteristic of the beam, with beam widths smaller than 1 degree, it offers a high spectral reuse with minimum interference, and it is more secure, being harder to detect and intercept. Here you may see the millimeter waves characteristics. Higher free space loss. Higher antenna gain. Narrower beam antennas. Low attenuation due to atmospheric gases. The peak at 60 GHz is due to oxygen absorption. High attenuation due to rain, which is the main factor that limits the effective link distance. So, for all the discussed reasons, the E-band represents a good microwave wireless alternative. The only drawback can be considered the relatively low distances for where the technology can be used, with radio links that usually fall within 3 miles, or lower. This makes it a very good alternative to traditional microwave, in the scenarios where radio links need to be deployed in highly densified large urban areas. This is why Ceragon uses millimeter wave products. Due to operational and commercial benefits for its light licensing, lower licensing fees, while still regulated, wide channels, high capacity, 1 gigabit per second. Due to physical characteristics, high spatial separation and high antenna directivity. Practically, no interference to the neighbors, hence, no spectrum congestion. Few kilometers distance with high availability, 99.995%. In the following chapter we will discuss about modulation, what it serves, what it is and how the system uses it. Modulation is the addition of information signal to a radio frequency carrier. Modulation is the process of modifying parameters of one signal based on another, for data transmissions. The parameters affected in modulation can be amplitude, frequency and phase of the signal. There are analog and digital modulation types. The analog modulation types are AM, amplitude modulation, FM, frequency modulation, PM, phase modulation. Most used modulation types in digital transmission are named with the shift keying process and the parameter being modified. ASK, or amplitude shift keying. FSK, or frequency shift keying. PSK, or phase shift keying. QAM, or quadrature amplitude modulation, the combination of phase and amplitude shift keying. Amplitude modulation is a method of impressing data onto a time-varying signal carrier waveform, digital signal in our case. The highest frequency of the modulating data is normally less than 10% of the carrier frequency. QAM is a method of combining two amplitude modulated signals into a single channel, at a quadrature shift or 90 degrees between them. The modulated signals are summed, and the final signal is a combination of both phase shift keying and amplitude shift keying. QAM is, simply said, a combination of amplitude and phase modulation for transmitting more data, easier. Here you may see the differences between ASK, PSK and FSK. ASK or amplitude shift keying changes the amplitude to the analog signal. 1 and 0 have different amplitudes. PSK or phase shift keying changes the phase to the transmitted signal. The simplest method uses 0 degrees and 180 degrees. FSK or frequency shift keying represents the two binary states 1 and 0 with different specific frequencies. In a quadrature amplitude modulation signal, there are two carriers, each having the same frequency but differing in phase by 90 degrees, 1/4 of a cycle, from which the term quadrature arises. One signal is called the I signal, and the other is called the Q signal. Mathematically, one of the signals can be represented by a sine wave, and the other by a cosine wave. The two modulated carriers are combined at the source for transmission. At the destination, the carriers are separated, the data is extracted from each, and then the data is combined into the original modulating information. Higher quadrature amplitude modulation is normally easier to generate and demodulate than higher PSK, because QAM can simply be formed from two orthogonally distanced amplitude shifted signals, whereas in higher orders of PSK, one needs better angle detection that is harder to obtain. The higher the modulation, the more capacity we have, as 4 QAM can carry 2 bits per symbol, 8 QAM can carry 3 bits per symbol and so on, up to 4096 QAM, that carries 12 bits per symbol. Quadrature amplitude modulation achieves a greater distance between adjacent points in the IQ plane by distributing the points more evenly. With the lower modulations, the points on the constellation are more distinct, at receiver, and data errors are reduced. With the higher modulation we have more bits per symbol, but the constellation points are closer, therefore the receiver is more susceptible to noise. I and Q modulation, aka quadrature amplitude modulation, is a method for sending two separate, and uniquely different, channels of information. As you know, the carrier is shifted to create two carriers, sinus and cosinus versions. The two modulation inputs, analog or digital, are applied to two separate balanced modulators, BM, each of which are supplied with the sinus or cosinus carriers. That is, modulator number 1 is supplied with the sinus carrier and modulator number 2 is supplied with the cosinus carrier. The outputs of both modulators are algebraically summed, the result of which is now a single signal to be transmitted, containing the I and Q information. This signal is for all intents and purposes a double sideband signal, DSP, with or without a carrier, reduced. This method of modulation has the advantage of reducing or eliminating intermodulation interference caused by a continuous carrier near the modulation sidebands. If you compare 4 QAM and 16 QAM modulation in terms of throughput and conditions, the 4 QAM has 2 bits per symbol and 16 QAM has 4 bits per symbol. So it means that in terms of throughput 16 QAM is 2 times higher capacity than 4 QAM. In terms of threshold, you can see that 4 QAM has just 1 point in each quadrant in the constellation diagram, and 16 QAM has 4 points in each same quadrant, so it means that 16 QAM modulated signal is 4 times harder to obtain and demodulate than 4 QAM. This is how the constellation diagram looks for a 2048 QAM modulated signal. While this seems very crowded, and it is, the modern radio transceivers in digital transmission can now operate with even higher, 4096 QAM modulations. The capacity will, of course, depend on the channel bandwidth as well. Adaptive coding and modulation, ACM, and the relation with mean square error, MSE. The Fiber IP20 platform employs full-range dynamic adaptive coding and modulation, ACM. With ACM on, the radio will select the highest capacity based on the received signal quality, represented in Ceragon network elements with the value of mean square error, or MSE. When the signal quality is degraded, due to fading or interference, the radio goes to a more robust modulation, dropping to lower capacity as well. The ACM mechanism can cope with 90 decibels per second fading in order to ensure the highest transmission quality. The ACM mechanism is designed to also work with the quality of service in each element, to ensure that high-priority voice and data frames are never dropped, thus maintaining even the most stringent service-level agreements. The hitless and errorless functionality of ACM has another major advantage in that it ensures that TCP/IP sessions do not time out. Without ACM, even interruptions as short as 50 milliseconds can lead to timeout of TCP/IP sessions, which are followed by a drastic throughput decrease while these sessions recover. When signal quality improves, the modulation is automatically increased and capacity is restored. The capacity changes are hitless, without errors being introduced. An ACM radio script is constructed of a set of modulation profiles. Each profile is defined by a modulation order and a coding rate, and defines the profile's capacity in bits per second. When an ACM script is activated, the system automatically chooses which profile to use according to the channel transmission conditions. The ACM transmit profile can be different from the ACM received profile. The ACM transmit profile is determined by the remote received signal quality, expressed by MSE value. The receiver end is the one that initiates an ACM profile upgrade or downgrade. When the MSE improves above a predefined threshold, RX generates a request to the remote transmitter to upgrade its profile. If MSE degrades below a predefined threshold, RX generates a request to the remote TX to downgrade its profile. Each radio profile differs by modulation order and coding rate, so there are different capacities per profile. Once again, the ACM transmission current profile is determined by far-end mean square error. Mean square error, MSE, is used to quantify the difference between an estimated or expected value and the actual received value. MSE is the average of the squared errors. MSE is an aggregated error by which the expected value differs from the quantity to be estimated. The difference occurs because of randomness and fading or interference. In order to understand better the mean square error concept, let's imagine a production line where a machine needs to insert one part into the other, so both pieces must match perfectly. Let us assume the dimension has to be 10 millimeters wide, but as in real life, we take a few of parts for audit and measure them to see how many can actually fit in. The Gaussian probability distribution functions represents the errors histogram. The accuracy of our machine is given by how many values differ from the expected value. As per our example, 9 parts were good but the rest not so much. To evaluate the inaccuracy or how severe the situation is, we measure how much the errors differ from expected value. We convert all errors to absolute values and then we square them. The squared values give bigger differences more weight than smaller differences, resulting in a more powerful statistics tool. As example, 16 mm parts are 36 units away than 2 mm parts which are only 4 units away. To evaluate the total errors, we sum all the squared errors and take the average. Total error equals 16 plus 9 plus 0 plus 4 plus 36 equals 65. So the average, MSE, equals total error divided by the number of errors equals 65 divided by 5 equals 13. The bigger the errors, or differences are, the bigger MSE becomes. MSE determines how narrow or wide the bell distribution is. When the MSE value is very small, the bell-shaped histogram is closer to perfect condition, that is a straight line which means 0 errors. However, real-life conditions look more like this distribution shown here, rather than a perfect line. In Ceragon machines, the MSE values are shown with decibels because of the large variances from expected to actual readings. Now to transpose to the MSE calculation for digital modulation. Let us use QPSK or 4QAM as an example. QPSK means 2 bits per symbol. 2 possible states for I signal. 2 possible states for Q signal. Resulting in 4 possible states for the combined signal, or 2 bits of information to be transmitted at every hertz. The graph shows the expected values, in a constellation map of the received signal level. The black dots represent the expected values of the received signal, RSL, as the blue dots represent the actual RSL. As in the previous example, the bigger the errors are, the harder it becomes to detect and recover the transmitted signal at receiver. MSE would be the average errors of E1 plus E2 plus E3 plus E4 etc. When MSE is very small, the actual signal is very close to the expected signal. We calculate MSE based on a large sample RSL. When MSE is too big, the actual signal, amplitude and phase, is too far from the expected signal. When the error is too big, we need a stronger error correction mechanism called forward error correction or FEC. Therefore, we reduce the number of bits per symbol allocated for actual data and reassign some of the bits for correction instead. For example, 256 QAM has greater capacity than the lower 64 QAM modulation but also poorer immunity to noise compared to 64 QAM, which has less capacity and it is more robust and therefore more immune to noise. An ACM radio script is constructed of a set of profiles. Each profile is defined by a modulation order, QAM, and coding rate, and defines the profile's capacity, bits per second. When an ACM script is activated, the system automatically chooses which profile to use according to the channel fading conditions. The ACM-TX profile can be different from the ACM-RX profile. The ACM-TX profile is determined by remote RX MSE performance. The RX end is the one that initiates an ACM profile upgrade or downgrade. When MSE improves above a predefined threshold, RX generates a request to the remote TX to upgrade its profile. If MSE degrades below a predefined threshold, RX generates a request to the remote TX to downgrade its profile. ACM profiles are decreased or increased in an errorless operation, without affecting traffic. In the graphic it is easier to observe the hysteresis of changing the ACM profile with respect to measured MSE. As you can see, the radio remains at profile 8 until MSE improves to minus 38 decibels. Here are the benefits of using ACM. To maximize spectrum usage. To increase the capacity over a given bandwidth, when propagation conditions permit it. To get more system gain, because the system can cope with approximately 1.5 to 2 decibels for each point change, meaning that the lower modulations will allow for more power throughput in operation. This functionality, called adaptive TX power, gets maximal system gain per working point. For hitless and errorless modulation changes, based on the radio signal quality, ACM also operates with an available quality of service mechanism for smart congestion management, which ensures high priority traffic is not affected during link fading. This chapter introduces the signal-to-noise ratio and bit error ratio concepts. The signal-to-noise ratio measures the difference between the useful signal level and the level of noise caught by the receiver on the transmission channel. In our presented example, we take the case of one modulation, QPSK to show you how the SNR level variation influences the bit error rate observed, which actually defines the quality of the transmission. Bit error ratio measures the ratio between the erroneous received bits and the total transmitted bits within that communication. In the first example, we can observe an ideal scenario, where no error bits are introduced. This is not a real-life scenario, just a theoretical one. In our second example, you can observe a small bit error rate of 10 to the power of minus 13, meaning that one error is introduced in 10 gigabit of transmitted bits. The third and fourth example show a higher bit error rate, with one error in 1 megabit and one in 1 kilobit of transmitted bits. The relationship is clear. The lower the signal-to-noise ratio, the higher the number of error received. We are showing this to exemplify the correlation between signal-to-noise ratio and the bit error ratio, which determines the link quality. The SNR values are not presented in Ceragon machines, but what you will see and utilize is the mean squared error values, in decibels, which follow the same correlation shown here. In today's digital world, bit error rate impacts the transmission quality as follows. For bit error rate of 10 to the power of minus 6, the voice communication is audible, and this is the minimum link quality for acceptance procedures with Ceragon elements. For bit error rate of 10 to the power of minus 5, the voice communication is considered barely audible and presents too many errors to commission a link. For bit error rate of 10 to the power of minus 3, the voice communication is very disturbing, barely understandable, and usually determines the link to break. As we have seen before, there is a strict relation between the bit error rate and SNR. Therefore, we can calculate a sensitivity threshold in terms of received signal level where we have the minimum of bit error rate of 10 to the power of minus 6. The difference between the nominal signal and the level of signal where a specific sensitivity and bit error rate can be achieved is called a fading margin. How much the signal can vary, while still keeping a desired minimum of quality, in other words. Each modulation has a sensitivity threshold for a specific bit error rate, that is according to the current SNR. If you think back to the constellation diagram, this represents the symbols in a constellation where original information can still be decoded, even if the symbol is close to a border with another quadrant and could be interpreted wrong. More specifically, the fading margin is the distance between threshold level and nominal input level, given by the path loss calculation. In the following chapter we will discuss about some of the most important transmission techniques, such as XPIC or cross-polarization interference cancellation, space diversity and line-of-sight MIMO. First off, let's discuss the cross-polarization interference cancellation, also called XPIC. As we can see in this graphic, we can have three ways of radio spectrum utilization in terms of channels, arrangement and polarizations. This applies for all microwave transmission vendors and is determined by the national regulation control organizations worldwide. Adjacent channel, common polarization, where all the channels share the same single polarization, either vertical or horizontal. Adjacent channel, alternating polarization, where adjacent channels are using different single polarizations, alternating them. Co-channel, dual polarization, where channels utilize dual polarization, both vertical and horizontal. Each channel is still determined by a specific central frequency and bandwidth. For the co-channel dual polarization spectrum utilization, the level of interference between two transceivers utilizing the same frequency on the two polarizations is referred to as a cross-polarization discrimination, or XPD. Cross-polarization interference cancellation algorithm enables detection of both streams transmitted on the same channel with alternating polarizations even under the worst levels of XPD such as 10 decibels. Fiber IP20 accomplishes this by adaptively subtracting from each carrier the interfering cross-carrier at the right phase and level. For high modulation schemes such as 1028 QAM or more, operating in a frequency of 28 GHz, an improvement factor of more than 20 decibels is required so that cross-interference does not adversely affect performance. The cross-polarization interference cancellation implementation. The cross-polarization interference cancellation mechanism utilizes the received signals from the vertical and horizontal modems to extract the V and the H signals and cancel the cross-polarization interference between these transmissions. The following figure is a basic graphic representation of how the signals involved in this process are sent, interfere with one another and get extracted at the receiver end, to obtain the double capacity possible, The H plus V signal is the combination of the desired horizontal signal and the interfering vertical signal, marked in lowercase, to denote that it is the interfering signal. The same happens with the vertical signal reception and the horizontal interfering one. The X-PIC mechanism uses the received signals from both feeds and manipulates them to produce the desired data. Fiber IP20's X-PIC mechanism reaches a bit error rate of 10 to the power of -6 and a code channel sensitivity of 10 decibels. The improvement factor in an X-PIC system is defined as the SNR at the threshold of 10 to the power of -6, with or without the X-PIC mechanism. Another mechanism called ATPC, used for controlling the output power of the transceiver when propagation conditions are good, is recommended to be turned on. Let's present a different perspective on the cohabitation of more than one signal on the same channel, with a different polarization. Presented here you can see a comparison of a system where no interference on the same channel is observed, on the left side diagram, and a system where we can observe a second polarization being used on the same frequency channel, on the right side. The noise rise observed on the right side is due to the cross-polarization interference when we add the vertical polarization to the same channel that was using the horizontal polarization. In our case, for these specific conditions, the interference creates a noise rise from -96 decibels all the way up to -65 decibels. This example comparison allows us to understand the need for an X-PIC mechanism. In this next slide, we are taking the last diagram from the previous, showing the interfered signal from a cross-polarization interferer and comparing it to a system where the same interference is cancelled by the X-PIC mechanism. This is how our systems allow for double the capacity to be transmitted over the same channel. When activating the cross-polarization interference cancellation algorithm, you may see in the right side of the picture the improvement of 26 decibels, that practically drops the interference level of the interferer over the interfered to -91 decibels. Therefore, with the help of the X-PIC algorithm, we improve the performance of a system that uses co-channel dual polarization, allowing for double the capacity to be used by the network element. Space diversity. There is a phenomenon called multipath, which affects the propagation of electromagnetic waves, more problematic for transmissions that happen below the 11 GHz frequencies. Multipath is the propagation phenomenon that results in radio signals reaching the receiving antenna by two or more paths. The causes of multipath include atmospheric ducting, ionospheric reflection and reflection from water bodies and terrestrial objects such as mountains and buildings. This happens more predominant on the longer radio links, which is exactly where the lower frequencies mentioned are being used by operators and microwave networks. As the multipath transmission is typically caused by fluctuating layers in the atmosphere or at ground level, the delay difference between the direct path and the reflected or deflected paths vary over time. Also, the reflection coefficient, that is the strength of the reflection or deflection, varies over time, resulting in erratic fading behavior. By putting a second receive antenna on the tower, with a vertical separation from the first antenna, we create a second set of delay combinations. In today's microwave radio equipment, two receivers, one for each antenna, are used to receive the signals and select the better of the two. The selection mechanism can be based on a switch which selects the better of the two received signals, or a more advanced technique where the two received signals are combined into one received signal. This last technique is called IF combining space diversity, and it offers a number of advantages. As a result, selective fading will occur at different times in the two received signals, one from each antenna, due to different delays. This combination of signals will result in a significantly higher probability of receiving an undistorted combined signal. The two receiver antennas will receive signals with different delays. As a result, if one of the two receivers should get a signal with a frequency notch, called distortion, it is very unlikely that the other will have a notch at the same time. If we then combine the signals received by the two antennas in phase, the spectrum notch will be significantly reduced. When a spectrum notch, or selective fading, appears on only one of the signals, the notch in the combined signal will be significantly reduced at this point. An additional advantage of combining the two received signals in phase is an improvement in the flat fading receiver threshold. The sum of two correlated signals, when the thermal noise in the two receivers is non-correlated, results in a 3 decibels lower bit error rate threshold if flat fading occurs simultaneously in both antennas. Space diversity configuration. Fiber IP20C's multi-carrier capabilities can be utilized to provide baseband combining space diversity. A space diversity configuration is based on either a 2x2 MIMO installation for 1+0 space diversity, or a 4x4 MIMO installation for the 2+2 hot standby space diversity, using 2 IP20C units. The antenna separation is based on normal space diversity requirements. In both space diversity modes, the transmitter connected to the diversity antenna is muted to achieve a configuration that consists of a single transmitter and 2 receivers. When IP20C is configured for space diversity operation, the signal is combined at the baseband level to improve resiliency to selective fading. 1+0 space diversity. The 1+0 space diversity configuration utilizes a single IP20C on each side of the link. The second carrier is muted. On the receiving side, the signals are combined to produce a single, optimized signal. 2+2 space diversity. 2+2 space diversity configuration utilizes 2 IP20C units on each side of the link, with both radio carriers activated in each unit. In each IP20C unit, both radio carriers are connected to a single antenna. 1 gigabit port on each IP20C is connected to an optical splitter. Traffic must be routed to an optical gigabit port on each IP20C unit. Both carriers of the slave unit are muted. On the receiving side, each unit receives a dual polarization signal from the remote master unit, which includes the data streams from both carriers. The slave unit shares the data stream it receives with the master unit, and the master unit combines each data stream to produce a single, optimized signal for each carrier. 2+2 space diversity provides equipment protection, as well as signal protection. If one unit goes out of service, the other unit takes over and maintains the link until the failed unit is restored to service and space diversity operation resumes. In effect, a 2+2 hot standby configuration is a protected 2+0 space diversity configuration. Each IP20C monitors both of its cores. If the active IP20C detects a radio failure in either of its cores, it initiates a switch over to the standby IP20C. Line of sight MIMO. Multiple input, multiple output. Line of sight multiple input, multiple output, or MIMO, is the latest leap in microwave transmission technology, enabling operators to double or quadruple spectral efficiency on the same channel. MIMO originated as a non-line of sight technology, exploiting signal multipath caused by reflections from various physical obstacles. It achieved this by using multiple transmitters and receivers to increase spectral efficiency, and by spatially multiplexing multiple bit streams over the same frequency channel. Line-of-sight MIMO achieves spatial multiplexing by creating an artificial phase to correlation with deliberate, planned, constant distance between the antennas at each end of the radio link. At each site in a line-of-sight MIMO configuration, data transmitted over the radio link is split into 2-bit streams in 2x2 MIMO, or 4-bit streams in 4x4 MIMO. These bit streams are transmitted via 2 antennas. In 2x2 MIMO, the antennas use a single polarization, while in 4x4 MIMO, each antenna uses dual polarization. The constant phase difference caused by the antenna separation enables the receiver to distinguish between the streams and allows for the capacity increase. The same signal will arrive at a different phase in different antennas. This is controlled by varying the path lengths. Path lengths are configurable by controlling antenna separation, H1 and H2. The following equation formulates the antenna separation distance required for optimal line-of-sight MIMO operation. When performing the installation, we always must be consistent with the separation between antennas at each end, either horizontal or vertical. Line-of-sight 4x4 MIMO is quadrupling capacity using the same channel bandwidth. So we can achieve 1 gigabit per second radio throughput over a single 28 MHz or 30 MHz channel bandwidth. Here are the MIMO benefits. Increased capacity. 2x2 MIMO enables transmission of 2 independent bit streams over the same frequency channel, using the same polarization, doubling the capacity of a single 1+0 link, which is the same capacity as an X-PIC link, but using only one polarization. 4x4 MIMO, with dual polarization, enables transmission of 4 independent bit streams over the same frequency channel, quadrupling the capacity of a single 1+0 link, at half the form factor. we can conclude that with MIMO you can upgrade the capacity without network replanning. Summary. In this module we have discussed about radio relay principles, modulation, adaptive coding and modulation, ACM, and mean square error, MSE, SNR and bit error ratio, transmission techniques such as cross-polarization interference cancellation, spatial diversity and line of sight multiple in, multiple out. Thank you for your attention.